Okay. Hi, everyone. Welcome to our next lecture. So today, as you can see, we're going to be talking about priors and giving an introduction to posterior analysis. So one of the things that we spoke about quite at length last week in the recorded session and then also in the discussion session that I hope you all enjoyed and were able to get a lot out of was about the use of and the importance of priors in modern Bayesian statistics and Bayesian analysis. And what we're going to be doing at the start of this lecture is continuing down that discussion of priors and what priors are, how you specify them and things like that, and how you specify them in a sensible way. And after that, we're going to then move on to an introduction of how you analyze posteriors. And that's going to be a very important lead in to what we're going to discuss next week, which is a lecture that I'm personally really excited and really looking forward to, which is all about Markov chain Monte Carlo. I think it's going to be a really useful lecture for you all, and I think it's also going to be a bit interesting and fun. So let's get started with what we're talking about today. What we're talking about is priors to start. So as we mentioned at the beginning of or during last week's lecture, when we were talking about Bayes' theorem, is that there's a fundamental difficulty, or one of the difficulties that we have when we're talking about, or you trying to use Bayes' theorem, is how we evaluate this integral that sits on the denominator. So you'll remember Bayes' theorem has this curly integral, which essentially gives us the probability of observing the data. And that probability of observing the data, x, requires us to integrate over all possible ways in which the data can be generated. Now, the way in which we visualized this last week was with our EARN model, where if we direct our attention to my little notepad here, we said if we take an example where we have an urn that's got some marbles in it, and let's say that this case there's 3 marbles of unknown color, and we want to basically know what is the probability, or what is the way in which I can observe some data. So let's say that the data is I observe one, say, black marble, right? Then the ways in which, the total different ways in which I can observe one black marble with, for example, one draw is 1 or 2, right? So it's 2 out of 3. That's the total possible probability of me observing a single draw of a black marble, right? And this becomes more complicated the more complicated the data are, and the more complicated the likelihood is, the more complicated the ways of generating your data are. And so this integral can be quite curly. And one of the ways that we can demonstrate how that integral can be a little bit curly is if we just take a pretty simple hypothesis, a pretty simple model, a pretty simple likelihood. So let's say that we have some set of data, right? That those data are X, and they consist of IID, remember this term, the independent and identically distributed observations from a Poissonian distribution with an unknown rate parameter theta. So the Poisson distribution, you'll remember, is a distribution that's governed entirely by this single rate parameter. And we don't know what that rate parameter is. However, our prior knowledge, our prior belief tells us that theta is definitely within the range of 0 and 1. Okay, so with these particular data, what we know is that for some physical reason, the range of possible values of our rate parameter theta in our generative function, the function that generates our data, is between 0 and 1. But all values within 0 and 1 are equally likely. We don't know anything about the possible values within that range. We just know that they exist in that range. The possible range of theta is in that range. So that means obviously that our prior on theta is going to be a uniform distribution. It's going to be a uniform distribution with probability of 1 between 0 and 1 and a probability of 0 otherwise. This is just a standard distribution that we've seen before. And in this setup where we have Poissonian data and a prior on theta that is a uniform distribution, we can calculate what our normalizing integral is, right? And that calculation is this. We just calculate the P of X, and it's the integral of P of theta times the likelihood integrated over theta. And just subbing in our different distributions. So we sub in the Poissonian likelihood, and we use our prior that takes us between 0 and 1, because it's only defined between 0 and 1. We end up with this integral for P of X. And that integral probably doesn't look like anything you're familiar with, and that's because it isn't anything particular. It's not an analytic distribution. It doesn't have a particular form that's nice. It is an ugly integral, and it can only be evaluated numerically, which means that there is no way of estimating the value of that integral without doing some sort of a computation, be that an estimate of the integral using an expansion, or using the trapezoidal rule, or using Markov integration, Monte Carlo integration, something we spoke about previously. So this is just a really simple demonstration of how even simple priors and simple data can lead to complex, awkward integrals on the denominator of this Bayes theorem. Right. So with that in mind, one of the things that we saw last week, or rather that I showed you last week, was that there are nice combinations of pairs of priors and likelihood. And the reason that those combinations are nice is that they result in posteriors that are totally analytic, that you can sample from directly, and that you can analyze directly. You don't have to worry about integrating, because these distributions are totally analytic, and often they integrate to unity because they're also probability distributions, like what we'll see in a second. With those combinations, those prior likelihood pairs, ones that are nice, or rather a particular class of ones that are nice, are what we call conjugate distributions. So we can describe what a conjugate distribution is. So let's define some distribution F, or rather a class of distributions F, that has some likelihood, that looks like P of X given theta, and some class of prior P. Okay, so we have our likelihood F and our prior P. The prior P is said to be a conjugate of the class of F if the posterior distribution is of the same class, is of the same form as the prior distribution for all possible data. Okay, agnostic to what we observe, if the class of the final posterior is of the same form as the prior given some likelihood F, then that FP pair is called a conjugate pair, or rather those two distributions are conjugates of one another. One of those such distributions we saw last week. So I actually gave you a little bit of a sneak peek of this last week when I showed you my priors for the three scenarios that we discussed. And though my priors in that setup were all beta functions, and you'll remember that the likelihood that we were analyzing was a binomial function. And those two distribution families form a conjugate pair. As it turns out, there's actually not a great deal of these distributions that form nice conjugate pairs. And all of them are of what we call the exponential family. That is, they all have a format of a likelihood that is of this form. It has some function h of x times some function g of theta times the exponential of t of x times c of theta. So where h, g, t, and c are all random functions, and those functions ensure that they integrate to unity, that the likelihood integrates to unity. So this is a probability distribution, and this is what's called this format is what's called the exponential family of probability distributions. So there's a bunch of examples of these. So the exponential, obviously. The Poisson distribution is of this family. The single parameter gamma distribution, that means that it's the gamma distribution where only one of the shape parameters is unknown. The binomial distribution is one of these family, and the Gaussian distribution, if the variance is known, is also one of this family. Okay, so if we have a Gaussian distribution where we know the scatter, the standard deviation, and we want to find the mean only, then that's also one of these. We can also use a conjugate analysis in that regard, in that circumstance. When we have data that follow one of these formats, provided there is no conflict with our prior belief, we can use one of these conjugate analyses to give us a perfectly analytic posterior and a perfectly analytic integral on the denominator. So some examples of prior likelihood pairs, prior likelihood conjugate pairs rather, are the ones that we've already seen. So we have the binomial distribution as a likelihood, and we have the beta distribution as a prior, and we end up with a posterior distribution that is a beta distribution, which has modified parameters from the prior to be p plus x for the first and q plus n minus x for the second. Now, if you go back to the notes from last week, we actually derived this without knowing what a conjugate pair was. And so you can go back and have a look at that derivation and just verify that this is actually what happens. Some other examples. So if we have the Poissonian distribution, then we can use the gamma distribution as a conjugate prior, and we end up with a gamma distribution. If we have a normal distribution with known variance, so tau here is a known quantity, then we can use a normal distribution as our prior, and we end up with a normal distribution as our posterior, okay, with modified parameters. We'll have a look at some of this in a little bit more detail a bit later. And finally, if we have a gamma distribution where k is known, so where we know one of the shape parameters, then we can use also a gamma prior. We end up with a gamma posterior. If k is unknown here, then that doesn't work for reasons that you can see yourself if you do the number crunching. Okay. So we spent a lot of time last week going through and talking about how important the prior is. I now want to take a brief detour to make it abundantly clear that the data is also important, because I feel like that's an important point to make. So we're going to talk about the role of data and what happens when you have a specific data set given an arbitrary prior. So let's consider a set of IID random observations, x1, x2, x3, all the way through to xn. And these are drawn from a normal distribution with unknown mean, but known variance. So known sigma. The probability distribution of the Gaussian with known variance is this thing here. So this is the likelihood of our observations. So we have, this is just the standard formula for your Gaussian, which you should all be familiar with. And from when we discussed it in an earlier lecture. And so the likelihood for these data, this is the probability of a particular datum given the parameter mu, the unknown theta. So the likelihood is the summation over all of the probabilities for a given theta. And that gives us this thing. The likelihood L is proportional to the exponential of the prefactor here times the sum of all of the values, or rather the squared residuals between the value of theta and all of our data. Okay, so again, probably shouldn't be anything that's too surprising to you. And we know from what we just saw on the last slide that we can use a conjugate here, which is going to be the Gaussian distribution with some parameter, mean parameter B and some variance C. Okay, so we go back and we specify that our prior knowledge is that theta is drawn from a normal distribution with B and C as the two parameters. And therefore, going back through our Bayes' theorem, the probability, the posterior probability distribution of this particular analysis, this particular setup, is this thing here is our prior, right? So again, just a normal distribution, but with parameters c squared and b instead of what we had up here, which was theta and sigma squared. And this here is our likelihood, which we just defined here. Okay, so this is just the unnormalized Bayes theorem, which hopefully you all remember from last week. We're now actually going to go through and crunch these numbers, because it's a useful task, and you should go through and do this as well in your own time. It's not a terribly difficult problem, this one, but it is fun to get your hands dirty a little bit every now and then. And it's useful because it tells us some really interesting things. It's some really important stuff. So if we combine the two exponentials, which we can do just by the multiplication rule for exponentials, we end up with this exponential here, which gives us the two terms. So this is, we've then expanded out the squared terms here. And we then group together. So we pull out a factor of -1/2, and we group together the terms of theta squared and theta into this term here, which is the theta squared term, and this term here, which is the theta term. We also end up with an additional term, or an additional couple of terms, which are the things that aren't related to theta, but because we've just got a proportionality here and those things are constant for a particular value of theta, we just throw them out. We just don't care about them for the moment. And so we end up with this exponential here. We then refactor this exponential by pulling out a factor of this thing out the front, and then compressing, or rather factorizing this expanded binomial here into this compressed notation, right? So theta squared minus 2 theta blah plus theta blah squared is equal to this theta minus blah all to the power of 2, and that blah here turns out to be this thing. So this is the second term, because we pulled out this thing at the front. Now, if you look at this distribution, the exponential of -1/2 times this thing multiplied by theta minus that thing all to the power of 2, that's just the same as our proportionality to the normal distribution, where sigma squared here is square root of 1 on that. And or rather sigma squared is 1 on that, and the value of the mean here, which is oriented there is a little bit confusing, is this big term here. And so what we can say is that therefore our posterior distribution follows a Gaussian, which has mean of this thing, which is this term here, and a sigma squared, or a variance of 1 on this thing here, right? Now that looks complicated. We can actually clean that up a little bit by defining two variables here just to make it a little bit neater. So we're going to define something here that we're going to call later on the precision, but the precision is just defined as 1 on the variance. Okay, so 1 over the variance is tau. So 1 over sigma squared is equal to tau, and d is equal to 1 over c squared. So this comes from our prior, remember, and this comes from the data. Right, our known variance in the data was sigma, and our prior variance was c squared. And that means that we now have a posterior that is a Gaussian that follows this form. So it has the mean bd minus nx bar tau divided by d plus n tau, and it has variance of 1 over d plus n tau. Okay. Why is this useful? Why is this important? Why are we going through this whole process? Let's take a moment to actually have a look at what we've just defined, what we've just derived. Remember now that tau is related to the inverse of the variance, right? So it's related to how accurately we know the data, okay? And d is related to how accurately we know the how confident we are in a particular value of the prior, right? That particular value being d, or rather, sorry, b, rather, from here. The prior, yeah. One sec. There we go. The posterior expectation, right, of this thing. So if we take the expectation of this thing, remember the expectation is just the arithmetic mean, right? If we take the expectation of this thing, what we find is that the expectation of the posterior is gamma nb plus 1 minus gamma n x bar. Now I've created a thing here, gamma n, which is d divided by d plus n tau. Okay. Now remember, d is the precision of the prior and tau is the precision of the data, right? So what that means is that the posterior mean, the expectation of the posterior, is a weighted sum of the prior mean, B, and the data mean, the data sample, X bar, the true mean X bar, or rather the sample mean X bar. And this weight parameter, gamma n, is determined by how strongly or how accurately we know the data and how strongly we believe in the prior. If n tau is very, very large compared to C, so or rather compared to D, the value of this thing goes to 0, right? Because this value becomes much, much larger than D. And so in the limit where NT is much, much larger than D, that is just NT over D goes to 0, right? So you end up with a gamma of 0, and the gamma of 0 means that this term becomes 0 in the expectation, and you end up with just X bar. So the expectation of the posterior in the limit where the data is much more precise than the prior is the sample mean of the data. I'll say that again because it's very important. In the limit where the prior knowledge is much weaker than the data, the posterior is determined almost exclusively by the data. And so the way in which we say this in Bayesian lingo is good data beats a bad prior. Okay, that's a very important outcome. The second, so there's a couple of other things. So the second thing here is that the posterior precision, so this reciprocal of the variance that I said here, the posterior precision is equal here, posterior precision here, to 1 over the sum of the data precision there plus the prior precision, right? So again, this is the thing that governs how narrow our posterior is, and it's related to how narrow the prior is and to how narrow the data is, which, objectively I think makes sense. As n goes to infinity, it's another important term. As n goes to infinity, if we look now at the first term, the mean, as n goes to infinity, the value of the posterior goes to X bar in the mean. So basically this term here dominates, right? So as n goes to infinity, that can be considered to be 0. And so you end up with n X bar tau divided by n tau. And those n taus obviously cancel, and you just end up with X bar, right? And so in the limit of large n, in the limit of many, many data, even agnostic to the precision, in the limit of large n, the posterior goes to the sample mean. So it doesn't matter if your prior is precise. In the limit of large n, the data always wins. Okay, so it's another very important outcome. So the prior has no effect in the limit of large n, or very little effect in the limit of large n. So again, good data, many data, beats a bad prior. Second lastly, as d goes to infinity, or as equivalently as c goes to 0, so as d, remember, it was just that conversion that we did here. So as the variance on the prior goes to 0. Sorry, as the precision of the prior goes to infinity. So the prior becomes increasingly imprecise, and we end up with a distribution that basically has a prior rather that is totally useless and doesn't give us any information. In the limit where the prior is very, very uninformative, or alternatively, in the limit where the data is much more precise, the prior has again no effect, because this again converges to the fact that n tau ends up being much larger than d, and you end up with the distribution of sigma squared over n and x bar in the mean. And the last point is sort of a minor one, but it's worth saying. The posterior distribution that we're showing here, this posterior, or rather this posterior up here, even in the limit of small n and an informative prior, is only dependent on x bar. There is no xi anywhere in this formula. What that means is that the posterior here for this setup is entirely informed by the mean, the sample mean of the data, and not on the any of the individual data themselves. And what that means is that x bar is what we call sufficient for the posterior inference theta. Said another way, if I had any sample of data that had an arbitrarily broad, actual true distribution, because of random noise, every single measurement that I made was actually a 6 sigma outlier of the truth. That doesn't matter if the distribution of those data has the same mean as a distribution of data that all sit within 1 sigma, because the mean is the only thing that matters in this particular setup. It's not necessarily true for all setups, but is true for this one. We can actually show, I didn't recompile this. We can actually show that this is true, that the majority, well, these more important things, in particular, this one here and this one here, we can show using something called asymptotics that this is true for any prior likelihood combination. When you specify, and the way in which we do that is we specify an arbitrary thing we call the loss function, and we'll talk about those again in a few slides' time. And we demonstrate that as you add more and more data, the probability that your estimated theta converges to the true underlying value of theta is basically guaranteed, regardless of what the prior is, provided, and this is a very, very big provided that the prior has non-zero probability at the value theta true, theta 0, whatever you want to call it. So that's the little side note that I just put in just before we started this lecture, which I put under there, but I forgot to compile it. So it'll be there in the lecture notes, but it's very important that you know that. So saying it again, the posterior, I'm going to draw it down here, the posterior of x, of theta given x, in the limit of large n, so as n goes to infinity, converges onto the estimate of theta converges on theta 0, right? Well, sorry, that x shouldn't be. Converges on theta 0. And where theta 0 is the truth, and it converges with absolute certainty, provided that the prior probability of theta, oops, shouldn't have put that bracket there, of theta at theta 0 is not equal to 0. Okay, it's that that factor there, that fact is very important, that the prior probability has to be non-zero at the truth for this to converge to the truth. Otherwise, it'll converge to something else, because your prior belief was that it is impossible for this parameter to be the truth. and therefore you can't recover that information. So it's an important caveat, but one that'll be in the lecture notes when you get them. Okay, one other thing that I wanted to point out here is a concept, well, that we've kind of just created without even realizing it. What we said up above was that our prior belief on theta was a Gaussian with unknown mean and unknown variance, right? Here, this thing here. This was our prior belief on theta. But then down here, what we said is that as the precision goes to infinity, right? As this thing, as the variance goes to infinity, the precision, goes to zero. I just realized I've got these letters flipped around. So as the precision goes to zero and the variance goes to infinity, that is that it gets broader and broader and broader and broader, the distribution of the posterior converges onto this parameter, right? So we said as our prior belief becomes very, very weak, our posterior converges on this value. But what we didn't recognize explicitly or otherwise is that a Gaussian with an infinite variance is not a probability distribution. It's not a valid probability distribution. And the reason it's not a valid probability distribution is because if your variance is infinite, then the probability of theta at any value of theta is of order unity, right? It's proportional to 1. Because if your variance is infinite, then you have a flat line, and that flat line doesn't ever get any shallower, right? It doesn't tail off at any point because the variance is infinity. Okay, and therefore it's a totally flat line. It doesn't have an end like the uniform distribution does. It just goes on for infinity in one direction and negative infinity in the other. And therefore it is a constant value. And what is the integral of a function that has a constant value from negative infinity to infinity? Well, it's infinity. And so by definition, this isn't a probability distribution because probability distributions have to integrate to 1. Okay, it doesn't make sense to have a probability that is greater than unity. And so this prior is not a valid probability distribution. We have violated one of the fundamental tenets that we said at the very beginning of this whole Bayesian statistics thing, which is that the prior should be a valid probability distribution. It should integrate to 1. But even though we completely violated that tenet, we ended up with a perfectly analytic probability distribution in our posterior. How does that happen? Well, it happens with some special types of priors, and those special types of priors, what we call improper prior distributions. So prior distributions that don't integrate to unity, or rather that do integrate to infinity, but that are totally valid in creating posteriors, are called improper priors. And they have some uses in particular places where you want to specify complete ignorance. So I have literally no idea about a parameter. It could be between negative infinity and infinity. I can specify an improper prior that has a single value of unity over proportional to unity over the entire number line and use that in my analysis. Sometimes it works, sometimes it doesn't. When we talked about, excuse me, when we talked about the normal mean example, we created this improper prior, which encoded the fact that our knowledge about the parameter theta was 0. We have no idea what it can be. And so we specified it as being a normal Gaussian distribution with infinite variance, right? The ignorance that we're trying to encode in that parameter, in that prior, is non-trivial. What do I mean by that? So when you specify an ignorant prior, when you specify a prior that says, I have no idea about the value of this parameter, that prior itself needs to demonstrate ignorance in more than just the simple one context that you're looking at. So we can take a really simple example. Let's take an improper prior that is of the form P of theta is proportional to 1. Okay, so it's that same improper prior we just defined in the last slide. But let's now modify our parameter to, instead of being theta, to instead be phi. And phi is just a simple transformation of theta. It's equal to theta squared. What does the prior on phi look like, given that we tried to specify complete ignorance in theta? Well, our complete ignorance in theta was of the form theta is proportional to 1. P of theta is proportional to 1. Our prior on phi, given this transformation, is just this thing here, the probability of theta squared times d theta d phi. And that thing there is proportional to 1 on the square root of phi. So by specifying a totally ignorant prior in theta and then doing a very simple numerical transformation to a different variable, we've come up with a very informative prior on phi. But if we have no idea about the possible values that theta can hold, then surely we should also have no idea about the possible values that phi can hold, right? And so we should equally be able to justify having a prior on phi that is proportional to unity over the entire number line. Okay, so with the improper prior, with our uniform improper prior, ignorance is not translated, is not conserved across parameter transformations, across scalings of the data. And that's possibly bad, right? Because if you have no idea about the value of theta, then you should also have no idea about the value of phi and da 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 da. And so one of the ways in which people have gotten around, or one of the ideas about getting around this particular problem of having a prior that is uninformative in one parameter and then accidentally informative in another, is by using what's called the Jeffreys prior. The Jeffreys prior is a concept that I think is important for you to understand. And it's based in a concept called Fisher information. I've misspelled Fisher there, I think. So the Fisher information is defined as this here. So the Fisher information of a parameter theta is given by the negative expectation of the second derivative of the log of the likelihood. Okay, so the second derivative with respect to theta of the log of the likelihood. Which is equivalent to this thing I've got down here at the bottom. If theta isn't just a single variable, if it's a vector of variables, then this thing changes slightly. This thing becomes the matrix of all partial derivatives, second order partial derivatives of all of the likelihood with respect to all of the different values, all the different vectorized parameters theta. And we'll actually see that in a minute in practice. So the Jeffreys prior, we've defined it as being this thing here. So, we've defined the Fisher information as being this thing here, and therefore the Jeffreys prior is this thing. P0 is how we demonstrate or signal that we're using the Jeffreys prior. And the Jeffreys prior of theta is proportional to the absolute value of this Fisher information, the square root of the absolute value of the Fisher information. Okay, and so, oh no, my thing is broken. Hold on, I want that formula to pop up, so I'm going to quickly recompile this. It only takes a second. All right, I think that should be there now. Yes, good. And so we can actually go back and I can show you here's my little comment about the asymptotics. So if you want to go back through and read that. Right, so where were we? The Jeffreys prior. So we define Jeffreys prior like this, and then we can actually just show the consistency of Jeffreys prior using a pretty simple demonstration just by actually doing a parameter transformation. Okay, so we can say that we've got some, we define some new parameter, phi, and that phi is some function of theta. It's a one-to-one parameter transformation of theta. We then have our simple change of variable formula. And what we know from our change of variable formula, as we saw above, is that the probability of phi is proportional to the now Jeffreys prior over theta times the absolute value of d theta d phi. Now, this thing here we just defined as being the absolute value of the inverse of the square root of the absolute value of the Fisher information. But by definition, from what we had up here, the Fisher information in phi is equal to the Fisher information in theta times d theta d phi. Okay, and what that means is that when we sub this back in up here, what we find is that the prior on phi is equal to the square root of the Fisher information in phi, which is the same thing as we had for our prior on theta. So the Jeffreys prior maintains the same value under parameter transformations. Okay, which means that the ignorance that we specify on theta is conserved when we now translate to a different parameter which has some arbitrary function of theta, and we call that function phi. So we can actually do this. We can actually just compute the Fisher, the Jeffreys prior and the Fisher information, and just see what this prior looks like in practice. So let's take, for example, a binomial. Oh, that should just say n. A binomial distribution of observations. So the likelihood follows a binomial. Therefore, the likelihood here is proportional to theta to the power of x, 1 minus theta to the power of n minus x. So again, this is just our binomial formulae. We have the log likelihood is then just taking the logarithm of this, and we end up with this formula here. And we can take the second order partial derivatives of the log likelihood, and what we find is we get this formula here. So this is the second order derivative with respect to theta of the log likelihood. We end up with this minus x over theta squared minus n minus x over theta 1 minus theta squared. And we can then take the expectation of this. So we take the arithmetic mean of this distribution, and the arithmetic mean of this distribution ends up looking like this. We get a couple of thetas cancelling, and we end up with minus n over theta minus n over 1 minus theta. Okay, so this thing here is the expectation. The reason we need this expectation is because that's what goes into our Fisher information. You'll remember back up here. Okay, so we've just calculated this thing here. And so our Fisher information is then, recalculating and reformulating this thing so that it's all smushed together. We end up with this formula here, which we can then simplify to n over theta times 1 minus theta. And therefore, the Jeffreys prior for a binomial distribution is proportional to theta to the power of 1 over 2. Minus the square root. 1 on the square root of theta times 1 minus theta, all again to the power of minus a half. So that's how we can calculate it for a single variable. But in our use, in our practices, single variables are pretty unlikely for us to come across. So let's actually think of a little bit more interesting case. Let's look at a case where we have two unknowns and we actually have to construct the Fisher information matrix. okay? Because the Fisher matrix is the more interesting part of this prior. So we have some Gaussian distribution where both the mean and sigma are unknown, the mean and variance are unknown, and that has a likelihood that's proportional to this thing here. Oh, my minus n has dropped. We've defined, I've defined just some variable s here to be just a simplification to make things a little bit easier. And using this likelihood here, we can define the Fisher information matrix I of theta as being the expectation of this matrix of partial derivatives. So on the diagonal, you can see the second order partial derivatives of, or rather the second order derivatives with respect to mu and sigma. And on the off diagonals, you can see the partial derivatives of mu and sigma and mu. And these all act upon the log likelihood. Okay, so we can go through and we can actually calculate each of these partial derivatives. So, or second order derivatives rather. So the second order derivative with respect to mu of the log likelihood is just equal to n sigma. So you can go through and do that yourself. With regards to sigma and mu, okay, so taking the partial derivative of sigma and then the partial derivative of mu with respect to mu rather, is the same as doing the inverse. And what we end up with is this term here. So the partial derivatives of sigma and mu is n times the sample mean minus the unknown population mean, or the distribution parameter that we're interested in, mu, all divided by sigma to the power of 4. And finally, the sigma, the second partial derivative with respect to sigma is this sort of long, complicated looking thing here. So we can then take each of these values, we can plug them in here, and we can calculate the expectation. Okay, so we plug all of these things here, we calculate the expectation of each, with the arithmetic mean of each one of these terms. And what we end up with is this pretty simple looking Fisher information matrix. So we end up with n sigma squared on the diagonal for the second derivative with respect to mu. We end up with n over 2 sigma to the power of 4 on the sigma squared partial derivative side. And we end up with 0 in the off diagonals because those terms disappear because they're small. And what we end up with is this Fisher information is proportional then to 1 over sigma to the power of 4. Okay, the higher power of sigma. We then take that particular setup, this Fisher value for the matrix here, and we can then say, because we know that the Fisher information with respect to theta is proportional to sigma to the power of 4, and the Jeffreys prior is defined, again, going back up to the top, as the Fisher information to the power of 1/2, then we end up with our final Jeffreys prior of mu and sigma squared is being proportional to 1 over sigma squared. So what did we just do? We've constructed a prior that is completely uninformative over various transformations that we might want to apply to the parameters that we're interested in, mu and sigma squared. And that uninformative prior, that Jeffreys prior, has a distribution that is just proportional to 1 on sigma squared. Okay, improper prior 1 on sigma squared, proportional to 1 on sigma squared. What's wrong with what we just did? So there's one major problem that people have with the Jeffreys prior. And that major problem is that it's based on the data. Because it uses the likelihood in defining the prior itself is being generated from what we think about the data, what we believe about the data. And that fundamentally goes against what we initially said, which is that the prior should be our belief about the parameters that we're interested in before we observe any data, right? Or before we even start thinking about the data, okay? And so because the prior here is related to the likelihood, it actually gets its information from the data distribution or the model that we think the data are drawn from, and that therefore influences the outcome. Right? And so that's the primary thing that people think is problematic with Jeffrey's prior. Okay, I know that was quite long. If you have any questions, that's totally understandable, totally fine. Feel free to ask them on the Slido. There are more complex or rather detailed discussions that we could have about priors, about different ways of specifying priors and things like that. So we can talk about things that are called maximum entropy priors, which are also to do with the Fisher information and how we actually maximize our amount of ignorance over different parameters. And there's things that we call reference priors and other things, but I've intentionally not included those in these lectures because I think that we're all a bit priored out. And given that the vast majority of our work is going to be defining reasonably simplistic, frequently uninformative priors, I think that it's not hugely relevant for what you're actually going to be doing day to day. If you disagree and you would like to learn about these things, then please let me know. I can very easily write these slides up, but I left them here as a note to myself to make sure to tell you that they're here if you want them, but I haven't written them. The last word that we're going to have on priors is about mixtures of conjugates. So let's consider going back all the way to the beginning to our simple coin toss. Okay, so we have our fair coin we just took out of our pocket, right? And when we flip that coin, overwhelmingly, the probability of getting a head or a tail is 50%, right? Because coins tend to be fair, general random coins, okay? However, if instead of flipping this coin in the air, I instead spin it on a countertop, on a tabletop, then little imperfections in the edges of the coin and the bumps of the table will mean that the outcome of that spin is likely to be a head or a tail more than it is to be completely fair, because the experiment that we're doing has imparted some additional bias on the outcome because of the imperfections on the side of the coin. So one thing that we might want to do if we've got an experiment where we're spinning a coin on a table is to specify that we don't think that it's going to be 50% of the time. We don't think we're going to get an outcome that's heads 50% of the time. We think it's going to be biased one way or the other, but we have no idea which way. We don't know if it's going to be biased to the positive, more heads, or to the negative, more, or to the slightly less than 50% more tails side. We just think our prior belief is that it's not going to be fair, right? Now, we know from what we've looked at already a couple of times that the coin toss and even the coin spin is going to be binomial. So the likelihood that we're interested in is binomial. And we want to do a conjugate analysis so that we don't have to worry about complex integrals and doing all that sort of stuff. And the conjugate of the binomial is the beta distribution, as we've seen again a couple of times already. But no beta distribution that we have allows us to have bimodality. There's no beta distribution that has a peak within the limits of 0 and 1. Multiple peaks within the limits of 0 and 1. So we don't have any binomial distribution that looks, like this, for example, between 0 and 1. Right? And so therefore, we can't specify a single binomial that accounts for our prior knowledge. Right? But we do have a beta distribution that looks like that. And we also have a beta distribution that looks like that. And therefore, we can supply multiple beta distributions combined together in summation that give us a prior that we're interested in, prior that we believe is an accurate reflection of our analysis, of our belief. And so we can use mixtures of these conjugate distributions to get the prior that we want and still end up with a conjugate analysis. So let's suppose we have some arbitrary mix of all possible conjugate distributions for a particular likelihood, right? So if this is the beta distribution, so if this is our case, we have binomial data and we have a beta distribution family of priors, this set here, P1 all the way through to PK, is the set of every possible beta distribution, every single one of them, okay? And every single one of those beta distributions leads to a slightly different posterior distribution. P1 theta of theta given X, P2 theta given X, et cetera, et cetera. Given each one of these posteriors, we can then, or rather, if each one of these priors, we can specify a particular arbitrary single prior distribution that is some weighted combination of all of the possible beta distributions. So if this, looking down here again, was our desired prior, then the weight would be 50% on the prior that gives us this first peak, 50% on the prior that gives us that, on the beta distribution that gives us that particular curve, and 0 on all other possible values of the beta distribution, right? So this summation then becomes quite simply, it's the first curve plus the second curve, right, is our prior. But given that arbitrary, weighted prior construction, we can then also construct our posterior. And our posterior just ends up being a weighted sum of the prior times the likelihood, which is just a weighted sum of the different posteriors that you get. And so I can trivially construct a posterior for my first distribution and a posterior for my first prior and a posterior for my second prior, and the posterior for my combined prior is just the weighted sum of those two posteriors from the two individual priors. And so I end up with a really simple mechanism for coming up with a posterior that is a good representation of, is an analytic distribution that I can sample from and that I can integrate trivially, but that can be fairly complex because I can add any number of different beta distributions and end up with some arbitrarily complex thing, but that is still analytic because it's a combination of beta distributions. Provided that that combination of beta distributions accurately reflects my prior information. If it doesn't, then this whole point is moot. Okay, hopefully that's clear. What we've spoken about for the last lecture and a half has been all about, with perhaps one exception, parameters and models where we have a single unknown. We have a single parameter that we're looking at that we're interested in, and we want to know whether or not that we want to try and infer something about that parameter. The reality of the vast majority of the analyses that we're going to be doing in reality in our natural sciences, in our academic careers, is that we're almost never going to be interested in one parameter. We're going to be interested in many parameters, many different unknowns that are all contributing to the physical system that we're trying to analyze. What we then want to do is try and construct a method for analyzing in a Bayesian or a classical framework, highly complex multi-parameter models. Now, this is another example, or at least one example, of where Bayesian stats is very, very powerful and much more useful and straightforward than classical statistics. If we have some vector of unknowns, so let's give it the symbol here, the vector, little arrow vector of theta, and it's equal, and it's got, you know, a series of k parameters, k unknowns, and we want to infer something about those k parameters. We specify some multivariate prior, which is a prior which has, you know, it's a multivariate distribution in all of the different possible values of theta. And we have some likelihood, that should be px given theta with a little arrow on top instead of tilde. And that gives us, so that's this likelihood here. And so then by Bayes' theorem, we have this posterior. Now you'll notice that the only thing that's changed here is the fact that I now have a little arrow on top of the thetas. Everything else in that equation is exactly identical to what we had previously. This is something that allows us, this is one way that Bayesian stats is much, much simpler than classical statistics, because we don't have to worry about coming up with a convoluted mechanism for creating a complex system that we can then analyze and fully translate the uncertainties, which is an important part, of all of the different parameters in our model into our final inference, because Bayes' theorem gives us it for free, because everything is treated as a probabilistic distribution. One of the ways that we can look at this is that we often want to talk about marginal distributions. We want to talk about, I want to infer the properties of a particular parameter. I know that my model has to include parameters for A, B, C, D, and E, but the only thing I care about for my science is the value of C, right? How do I infer, or what can I do to create inference about that particular parameter that I'm interested in? The way in which we do that is by constructing what's called the marginal distribution of the parameter in which we're interested in. And the way in which we do that is by integrating out all of the stuff that we don't care about. Okay, so we have some complex model, multi-parameter model that has many parameters in it, theta, and we observe some data, x. We have a complex prior of multi-parameters again, and then what we do after we've analyzed we've run our Bayes theorem, and we come out with our posterior. And this is a multi-dimensional posterior, right? It has a posterior distribution that is in every dimension of theta, right? But we only care about the parameter, say, theta 1, okay? And so what I can then do is I can integrate over all of the other parameters that I don't care about, all of the other thetas, to give me the probability of theta 1 given the data is equal to the integral of theta 2, theta 3, theta 4, all the way through to theta k of the posterior with respect to theta 2, theta 3, theta 4, theta 5, etc. That might look complicated, but the great thing about Bayesian statistics and the power of Bayesian statistics is that we can use posterior simulation to generate samples from the posterior, the n-dimensional posterior. So that whole thing that we spoke about a few lessons ago about simulating data, we can simulate data in our posterior space, in our n-dimensional posterior, which will give us samples from our n-dimensional posterior with values in theta 1, theta 2, theta 3, all the way through to theta k. But then we can just say, I don't care about the values of theta 2 through theta k, and just plot the histogram of theta 1. And that histogram is the marginal distribution of theta 1. It is the probability of theta 1 given the data. Okay? And that's really where the power of Bayesian stats begins to become really, really relevant to us. When we're talking about multi-parameter models, we generally have a few complications. One of those complications is how you specify the prior, okay? Because we've now got priors on theta 1, theta 2, theta 3, theta 4, all the way through to theta k. And we need to know how we're going to specify and how we're going to include the degeneracies and the crosstalk between all those different parameters. So multi-dimensional prior specification is more of a headache than you might naively anticipate. The computation of these integrals becomes even more complicated. I showed you at the beginning of this lecture how using a simple Poissonian distribution likelihood and a uniform distribution prior got us into a curly numerical problem. Now then ramp that up by a factor of k variables and things get much more complicated. And so we essentially always need complex numerical techniques to measure that integral. And the last thing is interpretation, which is what we're going to finish today's lecture with, which is about how you actually interpret the posterior distribution. How do you interpret the results? Right. So let's actually do this multi-dimensional posterior inference. Let's do it just for a simple example that I think you'll be able to follow. So let's say that a machine has either, we're in a manufacturing plant and we're manufacturing machines, and those machines are either made satisfactorily so that they can be sold, 1, or not satisfactorily so that they can't be sold, 2. The probability of it being manufactured satisfactorily is dependent on the room temperature during manufacturing and the humidity during manufacturing. The room temperature can either be hot, which is theta 1 is equal to 1, or cold, theta 1 is equal to 0. And the humidity can either be humid, theta 2 is equal to 1, or dry, theta 2 is equal to 0. The likelihood, so the probability that a machine is made satisfactorily given these different combinations of possible parameters is given here. So this is my likelihood. My likelihood of making a satisfactory machine given temperature and humidity is 60% if it's cold and dry. It's 80% if it's hot and dry, 70% if it's cold and humid, and 60% if it's hot and humid. Okay? I then have a joint prior distribution on the probabilities of whether it is going to be cold or hot or humid and dry. And the probabilities are these here. So there's a 30% chance that it's going to be cold and dry, 20% chance it's going to be hot and dry, 20% chance it's going to be cold and humid, and a 30% chance it's going to be hot. So given these two things, I can then calculate just with Bayes' theorem, can calculate the posterior probability, or rather the numerator of my Bayes' theorem. And the numerator of my Bayes' theorem is just the multiplication of these two things here, which gives me this matrix here. And then my posterior distribution is just this stuff here divided by the probability of x, which I haven't shown, but is just equal to 0.66. And the and then the which is just to do with the sum of these possible outcomes here, given the alternative, which is that you produce a bad machine. So the probability of producing a good machine is 66%. And so I end up with 18 over 66, 16 over 66, 14 over 66, and 18 over 66 for the different combinations here. Oh, this is broken as well. Having a bad run. And the marginal distribution that we're interested in then is asking the question, what does the probability look like of what is the probability that it was cold given that I produced a successful, satisfactory machine? Okay, that's what my posterior distribution here is asking. And that's what this number is here, despite what it looks like. And that is basically saying the probability of observing theta 1 is equal to 0, given I've observed x and theta 2, can be either 0 or 1, is basically just the summation of these two things along that axis, and that gives me 32 over 66. And so the probability that it was cold, given that I saw a satisfactory machine produced, is 32 on 66. Okay, so you can do this sort of game for multidimensional parameters, and we've just shown it here for a discrete problem because it's easy for us to visualize and to understand. But you can do this for much more complex distributions, and you can use exactly the same methods. You can use, for an arbitrarily complex continuous set of multidimensional parameters, you can use this to create posteriors in a particular parameter that are accurate, that are good reflections of our posterior, of our data given our prime, or of our parameter given our data rather. The question then becomes, how do I accurately infer something about the posterior that I have? And that's the thing we're going to finish with today, which is about summarizing posterior information. So this is where we're going to start talking about posteriors in length. And this is going to culminate next week with the probably more interesting stuff of Markov chain Monte Carlo. But to start off, there are a couple of ways that we can summarize posterior information. And one of the main ways in which we can summarize a posterior is by just having a single point estimate of our parameter theta. So the posterior gives us a full probability distribution of the possible values of theta. And for many applications, that full distribution is our inference about theta. We don't want to do any analysis, any further prodding or moving around with that particular distribution, because that is the thing that tells us the probabilistic values that our parameter of interest has. However, sometimes thinking in terms of a full probability distribution is complicated, especially when that full probability distribution might be multidimensional, or where we're interested in using a best estimate of a particular parameter for some other analysis. So the question then becomes, how do we define a best estimate? So the way in which we can do that is by specifying something we call a loss function, which basically penalizes the value of our estimate of theta, given the locations of all of given the distribution, the probability distribution of our posterior. There are lots of different potential loss functions, and a few of them that we've already actually seen, I'm going to talk about. So one of them we've already seen is the quadratic loss. So we specified this when we were talking about the standard deviation. So the loss function is defined as the value of the loss function for a particular combination of theta and A, where A is just some individual value along the number line, is equal to theta minus A all squared. The absolute error loss we've also seen is the absolute value of theta minus A. The 1,0 loss is something that we haven't seen before, which is another type of loss function. That is, if theta is within some tolerance epsilon of A, then the loss is 0. And if it is greater than that tolerance, then the loss is 1. And the last is the linear loss, which is specified for some arbitrary function G and H is greater than 0. Some arbitrary value G and H is greater than 0. The linear loss is defined as G times the difference that we have for values of alpha, A is greater than theta, and H times the difference that we have for A is less than theta. We can then calculate the best value by minimizing the loss of each of these different functions, right? And each of these different loss functions will give us a different best value. And which one you pick, which one is the actual best value that you want to use, is essentially up to you. It depends on the method, on the analysis you're doing, and what you're worried about, or what you want to use the data for, the best estimate for. But I'm going to give you a couple of examples of what these loss functions give you. And I know that some of you are probably thinking, well, I'm just going to take the mean, so this is all a waste of time. We'll see why in a second. So the way in which we can calculate the best value is by calculating the expected loss, which we'll just call rho of A given X, given some posterior distribution P of theta given X, right? So the expected loss, rho, is the integral of the loss function times the posterior, all integrated by theta. So if we're using quadratic loss, we can actually just do this integral, which I've done here, and I'll let you go through in your own time. But the end result is that the quadratic loss is the integral of the expectation of the quadratic loss is this thing here. It's the variance of the posterior plus the expectation of the posterior minus A all squared. Single bracket. Okay. Now, this thing here must be minimized because this is all squared when A is equal to the posterior expectation. Because otherwise, this thing is non-zero, and the quadratic loss gets large, right? So this thing is minimized when A is equal to the expectation of the posterior. What is the expectation of the posterior? It's the mean. Therefore, the quadratic loss is minimized when the best estimate is the mean of the marginal distribution of the posterior. So to everyone who is thinking, I'm just going to use the mean, you're actually minimizing the quadratic loss, which is probably not surprising because you'll remember that the way in which we defined the arithmetic mean was using the quadratic loss earlier on in the lecture course. There are other outcomes that we can get, so we can play the same game with the linear loss. So the linear loss, you'll remember, was the last one here, and I've skipped straight to the linear loss because the absolute error loss is actually just a special case of the linear loss where G and H are both equal to 1, which is why you get this absolute value. And you end up with, so we have this special case where G and H is equal to 1. But let's just look at the generic linear loss for a second. We can define some quantile of the loss function, let's call it Q, and the H over G plus H quantile of the posterior distribution is defined as this. So this quantile here is defined as the integral from minus infinity to that particular quantile of the posterior distribution. This is just the same definition as the quantile function that we've looked at before. And if we have A is greater than Q, then we have this difference here for two values, A and Q. And if Q and A wrap the parameter estimate theta, then we end up with this relationship here, this inequality here. So the, which again, I'll let you go through and crunch the numbers on this in your own time. But all you need to recognize is that because we have this reflection here around the parameter estimate, when we have this situation, so the Q is less than theta is less than A, we end up with this formula here for the difference between the quadratic, the linear loss between for some quantile Q and some estimate A, some estimate of the parameter A. And that means that we can take the expectation of this thing and we then, do some clever inequalities here. And what we find is that the expected loss for a particular parameter, for a particular value, A, okay, is greater than the loss for some quantile given that particular value of A for all A, right? And so if we set A is equal to Q, because that's the minimum, right, where Q and A equal one another, then the H over G plus 8th quantile of the posterior distribution minimizes this loss function. Okay, so if you set Q is equal to A in here, then what you find is that the minimum is when you're at that quantile, and that minimizes the linear loss for an arbitrary choice of H and G. Now, if we're in the special case of where H and G are both equal to 1, which is the absolute error loss, then that means that we have 1 divided by 1 plus 1 which is 1 divided by 2, which you get your calculator out, is a half. The half quantile of a half is the median. That's what we define the median as. It's the 50th percentile of the distribution. And therefore, going back up here, the absolute error loss is minimized at the median of the posterior. So the quadratic loss minimizes the mean. The absolute error loss minimizes at the median. Okay, so these are the reasons why people justify themselves as saying, I'll just take the median of the posterior, or I'll just take the mean of the posterior. It's because what they're actually saying is, I know, even if they recognize it or not, that the quadratic loss and the absolute error loss are being minimized in those two choices, and that's the thing that I care about. We can play exactly the same game for the 1-0 loss, and we can use the 1-0 loss to define an interval which is governed by this value epsilon. And that interval is minimized. So the size of that interval is minimized when the interval sits around the peak of the distribution, the posterior, right? So you can just imagine that quite obviously. If you look at my notepad here, if the posterior is one-dimensional and it looks like that, the minimum interval, the smallest possible epsilon that minimizes the loss for a particular choice the value of A that minimizes the loss here for a particular size of an interval, epsilon, is when A is at the peak of the distribution. Okay, because the most mass contained within a particular interval is going to be located around the peak of the distribution. This is true if the peak is heavy-tailed, or if it has, lots of funny stuff going on. So long as you're looking at the peak of the distribution, that 1-0 loss is going to be minimized. And therefore, the 1-0 loss minimizes at the mode. Okay, so for an arbitrarily small epsilon, the 1-0 loss minimizes the mode. And so these three loss functions minimize at, respectively, the mean, the median, and the mode of the posterior. And so whichever one you pick as your estimate for the parameter that you're interested in is totally justified, depending on what type of loss you want to use, what type of loss function you want to specify. The thing we're going to finish on today is about how we can use, let's say, instead of not wanting to have a particular single estimate, it's much more sensible for us to have a range of probability, rather an interval in which we can say there is an n% chance that my parameter resides within this range of values. And then define that percentage as being 60% or 95% or whatever we want. So this is what we define as what's called the credibility interval. It's something similar to what's called the confidence interval in classical statistics, and you should be clear on the distinction. There's no such thing as a confidence interval in Bayesian statistics. There is a credibility interval. The point estimate gives us no measure of the accuracy with which we know a parameter. So take an example of the 1-0 loss. So let's look again at my distribution here. And let's say I have some parameter, some range of possible values, some posterior here. Okay, this is my posterior, P of phi given X, and this is X. And let's say, phi. And let's say that the posterior distribution looks like this. Okay, so it's some very, very broad, very, very shallow distribution. And let's say then that I take the mode as my estimate of the point, the point estimate. Okay, so that means that my estimate of theta is this thing here. It's called theta hat. But I have no idea of how accurately I know theta hat, or how accurately, theta hat is known. And so what we really want to do is we want to specify some region which defines a likely area in which theta is to reside. Okay, and that's the credibility interval. So this concept, doing this in classical statistics, is quite difficult because the probabilities are treated as certain quantities. They're not random variables. So the value of a particular, or the likelihood of a particular set of data given a value of theta is constant, right? So the theta values are all treated as constants, and therefore it's very difficult to say that there is some probability of theta being this range of values. But we don't have that problem in Bayesian stats, and we can define some confidence interval, which is just the region of the posterior that contains 100 times 1 minus alpha % of the probability mass. So again, I can draw a random PDF. Let's make my random PDF look like this. Okay, so this is my random PDF. And what you can see is that my random PDF is complex, okay? And I can define a credibility interval that contains n% of that thing. So let's say I want to define a credibility interval that contains 10% of that particular PDF. You immediately realize the slight problem here, which is that 10% of this distribution can be anywhere, right? I can define 10% as being this 10%. Let me zoom out a little bit. This 10%, just here. Or I could define this 10%, just here, right? Or I can define that 10%, just there, right? So the value of a particular number of percent is a totally arbitrary value, right? It can be anywhere. It slides, and its size will change as I slide along the x-axis, but its value can be anywhere. And so generally what we're interested in talking about is the most probable value. And so what we do is we construct a credibility interval that is that has an amount of probability that is greater than alpha, right? So we still want to define a probability, let's say 10%, but we want to define our credibility interval as being the values of theta where the probability is greater than some value. So we're doing a horizontal slice through the PDF. And we're saying I want to make my confidence interval the place at which, or the region at which, that slice contains 10% of the data, right? And that naturally produces what's called the highest posterior density, right? The highest posterior density region. So this is obviously more than the percentage that I said with my little line here, but let's say that I was doing, I don't know, 30%. Then this here would be my credibility region, C alpha theta, right? That region in the middle there. Okay, because I've used the highest posterior density to specify my location for my credibility interval, and then I've made my cut. Okay, so I know that it contains 30% of the data, but I also make sure that that interval is as narrow as possible. And generally, we find that value, that region, analytically, numerically rather than analytically, because it's difficult to find, if not impossible to find analytically. All right. There is another section here that is on predictive distributions. I think that we can probably, we can probably talk about that next week, the beginning of next week. It's not unrelated from the start of the Markov chain Monte Carlo stuff that we're going to be talking about. So let's worry about that next week. And yeah, I know that was quite a math heavy and theory heavy lecture. So my apologies for that. It was bound to happen in a statistics course at some point. But fear not. Next week, we're going to be delving into what I think is probably one of the most interesting parts of the course, which is Markov chain Monte Carlo, as I've said before. And I think is probably one of the most useful parts of the course in terms of your own statistical knowledge and what you'll end up using in your day-to-day academic lives over the course of the next, however many years. So thanks again, everyone, for coming along. If you have any questions, please feel free to either hang about after everyone leaves and ask them to me directly, or post them on the Slido as you would like. And we will meet again next week to discuss posterior, the posterior predictive distributions, and start looking at MCMC. So until then, thanks very much again, everyone, and enjoy the weather.